So here I want to do problem 1223. Here we have a beam that is supported by a hinge attached to a wall, as well as a cable attached to a wall, making an angle theta here and the same angle theta here. The first step in doing equilibrium problem or statics problem like this is to draw a detailed force diagram of the object of interest. The object of interest here, of course, is the beam. Now, the force diagram is not a free body diagram. It will be a simplified, idealized version of the actual picture. So here's the picture that we have, and here would be its force diagram. There's the tension in the cable T, the weight which acts on the center of mass at the center, so at the half of the length of the beam, and then two forces. We've broken it into components, the horizontal component and the vertical component. These forces represent the force of the hinge on the beam. By the way, they give us theta as 30 degrees, but for now let's just keep theta as a symbol, because in other kinds of problems theta not be so nice and not such a nice angle. So one thing we see is if this angle here is theta, which is the angle between the vertical and the cable, then this angle over here between the vertical and the cable here should also be theta. Now we're ready to apply Newton's second law for linear and rotational motion to keep this beam stationary and in equilibrium. So the second step is to balance the forces in the x direction by applying Newton's second law. Sum of the forces in the x equal to 0. Looking back at our picture, we see that there are only two forces in the x direction, F sub h and the horizontal component of the tension, as in this picture showing Tx and Ty. So putting it in the equation, Fh is positive because it's going to the right, and minus Tx, negative because it's going to the left. And then we put in for what Tx is, which is T sine theta, and then we solve for Fh. Similarly, we can go to the third step, which is summing the forces in the y and setting them equal to 0. Here we would have F sub v, which is positive, minus mg, the weight, negative, and plus ty, positive. Now, sometimes you might not know if a certain force is positive or negative. Just draw the forces in any direction, choose it, and in the end the sign of that force will tell you whether it's the same direction or opposite to what you chose. Now we can put in for ty, which will be t cosine theta now. And solving for f sub v, we get f sub v equals to mg minus t cosine theta. The fourth and last step is to sum the torques and set it equal to 0. Before we can do that, we should choose an origin. We should choose an origin that eliminates the most torques. So looking at the picture, we potentially have 4 torques because there are 4 forces. But if we choose the origin to be here at the hinge, then we can get rid of the torque due to Fh and Fv because there's no radius. They're both acting on the point of the origin. So we only have 2 torques left from the weight and from the tension. Of course, we're only interested in the perpendicular components of the forces, mg perpendicular, and the perpendicular component of the tension, T perpendicular here. So writing out the sum of the torques equals 0, we have minus mg perpendicular times L over 2, minus because the mg perpendicular wants to rotate the beam in the clockwise direction. Another way to look at it is we want to take r across f. This is r, and if you curl your fingers towards f, we have your thumb will be pointing into the page. That's why there's a minus sign. So mg perpendicular, and then times r, which is, since it's in the middle of the beam, it's L over 2. the torque from the tension is going to be positive because it wants to rotate it counterclockwise, or R across F gives your thumb going out of the page, and the radius in this case is the whole length of the beam, L. We can put in for what T perpendicular is. It's just going to be T sine theta. To get G perpendicular, we notice that this angle between the beam and the vertical is 2 theta. That means this angle is also 2 theta, which is shown in this picture, which means that G perpendicular is going to be the sine of 2 theta. And putting it in, we can now solve for T by bringing this term over to the other side and then cancel the L's here to get finally T equal to mg over 2 sine 2 theta over sine theta. Now since sine 2 theta is actually 2 sine theta times cosine theta, we can plug this in and finally get a very simple expression for the tension, mg cosine theta. To get the final answers for FH and FV, we want to take this value for T and plug it in to our previous expressions for them. And if we do this, we get the following for FH and FV. Okay, that's it. Bye.